Hi class, today we have a rather interesting lecture on classification algorithms. As we've seen in the introductory class, there are different tasks that we can tackle with data science. We have classification and regression, perhaps being the most known ones, but other things like clustering and similarity matching. This week, we're going to be focusing on the very first one, classification. So what is classification? I always start by taking a dictionary, and classification there is listed as the act or process of dividing things into groups according to their type. Simple enough, right? So let's have a look at an example. This is one of the very early applications of classification back in the 90s. Is an email spam or not? Okay. If we look at an email, the algorithm will have a look at certain things. Actually, even if you look at an email, what would make you think this is spam or not? Okay. You can look at the address. It's impersonal. There's no name, so it might be mass emailing. Are there any suspicious links? Here there's a link asking for a password, basically. And if you check, the domain name of the link isn't quite kosher. The same with the email domain. It looks like it's from S2TD, but it's really not. Okay. So these are sort of our input variables or features that we will use to make determination spam or not. Other examples of classification, this is a very typical one. This is one that we'll be doing in the lab. Is this a cat or a dog? It might be the lab on convolutional neural networks, actually. Okay. Images can just as well be inputs to our algorithm. Is there a traffic jam or not? This is something I think they implement in the Causeway and Jurong, where they just look at the images from the traffic cameras and they'll determine the amount of traffic there is. Okay. Other examples include movie reviews, so based on input text, is it positive or negative? What is the species of this plant? I have this app on my phone. You can scan like a tree and it'll tell you what type it is. Where was this message sent from? What genre does a song belong to? Will a song be a hit or not? Many, 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 many more examples of classification tasks exist. Okay. If we look at the input, we can have different types. So we could have text, audio, images, videos, and probably forgetting some signal time series, sensor input, etc. So I think last week in the lecture and lab, you should have practiced a little bit on how to deal with different types of data, such as text. But we're going to be focusing on each of these modalities more in the future lab. So we'll have a lab on convolutional neural networks, which will focus on images, but might as well work on audio as well. And we'll have a lab on NLP, Word2Vec, which focuses on text. How you represent them in the end doesn't make much difference. The algorithms that you will be using will be the same. So we'll have a general approach to classification tasks. We will have a training set and a test set. So we're splitting up our data set. And this is a typical split here. We have about 2/3 for the training set and 1/3 of the data for the test set. Okay. Honestly, I think this works, but the more valid approach would be to use something like tenfold cross-validation. This is something that we'll talk about in a little bit. Okay. Tenfold cross-validation, just to mention, we basically splitting our data, or they say k-fold, but in case k is 10, we have split our data set up in 10 parts. We use one of the parts for test, the others for training. And then we do it again. We use one for test and the other for training. Do it again. And we do this 10 times. until finally we get 10 results and we average those results. Okay, so that is actually the most honest representation, because you could cherry pick whatever is in your test set so that your results are as good as possible. Okay, this is something that you shouldn't do. It's bad practice. Okay. All right. Anyway, so we have our training set, we have our test set. Training set is used to induce your model, to learn your model, train your model. So for that, you use a learning algorithm. This results in your actual model, and then we can use this to infer or deduce the class of the items in your test set. And then typically we will test, because we have the actual label for this test set, we will test how good it is, what is the accuracy, AUC, and all these things we mentioned in the first class as well. Okay. Right. So if we look at a more formal definition than the dictionary, we can see that classification is given a collection of records, which we refer to as a training set. And each record is characterized by a tuple xy, where x is the attribute set, so the feature set, all of the different input features, and y is the class label. We're trying to learn a model that maps each input attribute x into one of the predefined class labels y, and now I'd say with the greatest accuracy, recall, precision. Okay. So we have many types of techniques that we can use to learn these models. Some base classifiers, decision trees, rule-based models, nearest neighbor, logistic regression. I find logistic regression super simple and very effective. Naive Bayes or other Bayesian models. Support vector machines, usually called SVM. You've come across them. Then we go into the neural network stuff and deep neural networks, which are basically neural networks with more than one or two layers. These we will see, Prof. Sujanya will go over this with you in 2 or 3 weeks, 2 or 3 lecture weeks. And we will build upon this once we sort of start the second half of the class. We'll go more into neural networks, word-to-vec, convolutional neural networks, LSTMs, etc. But we want to make sure you have a strong knowledge of these basic as well, because I think these days too often we just ignore these classical methods. Okay. I should also mention ensemble classifiers, because these actually work pretty well often. There's ways of combining the output of several of these algorithms and making them into a stronger classifier. So we'll talk about that one as well. So which classification methods should we use? You might think we just need the one that gives the best predictions. Okay. Does that mean it gives the best predictions on the training data? Because then we would probably be overfitting. If you think about it, I have, let's say I have 3 variables, input variables, x, 1, 2, 3, and I need to predict y. Let's say if x is 2, 3, and 1, x would be 100. If I make a rule-based model, I could say if x1 is 2 and x2 is 3 and x3 is 1, then y equals 100. Okay. Then I would have 100% accuracy on the training set. This is important, training set. But it probably wouldn't work on new data. So you'll be overfitting. So you don't want the best prediction on the training set. You might want the best prediction on the test set, data that the model hasn't seen yet. Or sometimes there's even a third set, which we refer to as the validation set. The validation set is sort of part of your training set, but you use it while you're training your model. So if you're using a validation set, you would have your test set. So you'd have your training set, you have your test set, and you use part of the validation set part of the training set for validation, meaning that while you go through a training loop, you use this one to see if the parameters of your model are okay. And you're going to tweak the parameters to optimize not just for the training, but also for the validation set, okay? So this usually prevents overfitting a little bit. More on detail for that later. So, best prediction, is this something you want for your model? Perhaps, but perhaps not. Maybe you have a huge amount of data and you actually want the model that is most computationally efficient. But does that mean that the training need to be fast? Training is usually what takes longest. Or does that mean that the classification, the actual inference, should be fast? Do you want an interpretable model? So if you're looking at banks use machine learning to do credit score estimation. So based on all your history, your spending history, your balances, bank's model will say you are eligible for a loan or not. Okay, it's great. But if they have a black box model and it says you can't have a loan, and they tell me this, then I'm going to say why. And in fact, finance laws require banks to be able to explain and have valid reasons why they reject somebody for a loan. So they cannot use a deep neural network. They need something like a rule-based method, so they can say, your credit card balance has been under 10,000 for this period. Okay, that is a reason that they can give me, and a rule-based model or a decision tree model will give you those rules, whereas a neural network wouldn't. We might also want a model that's easy to implement so that we can do fast iterations. Again, we can wonder, is it easy to implement the learning process or the classification process? Okay. So it's not sort of I'll go over all these classification models and then by the end of the class you'll know the best model and that's the one you use. No, you have to sort of try all of these models. Okay. And if you were to work as a data scientist, you'll know that data science involves analyzing, making multiple models, comparing their performance, and being clever about highlighting their pros and cons. That being said, let's go over all of the models, starting with decision trees. Okay. Here's a picture of a very small decision tree. As you see, it consists of nodes. The square boxes consists of branches and leaves. Okay. The leaves will be our eventual predicted classes. The nodes will be tests of a value, meaning of an attribute, and the branches will be the respective values that we're testing for that particular attribute. Okay. In this case, homeowner, yes or no. We're testing here to see, or we're training a model that can predict if someone is a defaulted borrower, yes or no. If someone is a homeowner, then the model predicts they won't be a defaulted borrower. Let's have a look at our training data. Their homeowner is yes, indeed. Yes, indeed. Yes, correct. So, the decision tree here found a rule that that is correct for a part of our data. Then, when they are not a homeowner, then we check marital status. If they're married, then they also will be a default borrower, indeed. Married, okay. Married, no. Married, no, indeed. Identified another rule. So you can see how this works. This works with binary attributes like homeowner. It works with I would say categorical data, but it's also binary. Oh, no, it's categorical data. There are 3 classes, marital status. It also works with numerical values, although we have to bin them. What does that mean? We have to create a split. In this case, the income is lower than or higher than 50,000. Okay. So then we have a new attribute from our test set, sorry, not attribute, instance of our test set, and we can simply test to see if they will be a defaulted borrower or not. Their homeowner, no. Okay, easy. They will not. Oh, sorry. Their homeowner, no. We go here. Merit, they're married. So no, the prediction is no. Okay. Simple enough, this decision tree. Okay. Here's another example that emphasizes. It actually looks very much like the same example. Okay, it emphasizes that we can have categorical classes, binary or continuous, and then finally we have a class, which usually is a categorical variable. Okay. So the thing with decision trees is there can actually be more than one tree that fits the same data. Here, actually, we see that while the problem is the same, the marital status and the homeowner attributes are switched, and the tree has the same amount of precision even. So there's not one solution, there could be multiple. When we apply a model to the test data, we start from the root of the tree and we fill everything in. We just did that. Homeowner, no. Marital status, married, so prediction is no. Okay, easy. Right, so we learned the tree from the training model to get a model, from the training data to get a model, and then we can apply it to induce and predict the class. Now let's focus a little bit on how do we induce the tree from the training data set. There are many algorithms for this. One of the earliest is Hunt's algorithm. There's CART, I3, which is iterative dichotomizer 3, C4.3, quite efficient one that I've used in research. Slick, Sprint. Let's go over a few of them so you understand the principles behind decision tree induction. Here's Hunt's algorithm. Let dt be the set of training records that reach a node t. Okay, so it can be, it's our first time we do this, so it can be our root node. So we have dt being our full data set still. dt, which attribute do we need to put in this node? Okay. If dt contains records that only belong to the class yt, so it's a particular class, then it's the class that occurs within the dataset dt. Then t is a leaf node labeled as yt, so that would be easy. If this subdataset dt contains records that belong to more than one class, use an attribute test to split the data into smaller subsets, and then recursively go through these steps. So in the case that this happens, what does it mean? Well, let's take a look. Let's say that this instances would be in dt, then dt will become a leaf node. Okay. How can this happen, you think? Because this is our root node, so it wouldn't happen yet. It can happen because each time data is covered by a rule, it's sort of removed and your dt becomes smaller. Sort of like in our example, when we said we're looking for homeowners, here we had homeowners, yes, those basically were all covered by a rule, so they're removed, were covered by this, so they're removed and our dt will exclude these instances. Okay. And in that case, in the case that we'd only have no as a class, then we would be at a leaf node at the end of a tree. If there's more than one record, then we have to use an attribute split. Attribute test. So just to summarize the structure of Hunt's algorithm, you're at a certain node, you consider all of the instances that reach that node as your training set dt, and then If all of them belong to the same class, great, you have a leaf. If they contain records of more than one class, you use an attribute test to split the data, as we will talk about in the next slides. Then once you have decided on this split, what you do is you look at the next node, and you're basically going to remove all of the training sets, training records, or instances that are covered in other nodes from your dataset, and your dataset DT is going to be smaller now. So to determine the best split, you have to try a few attributes and then specify the attribute test condition. Okay. So you need to make two decisions. Like in the case of this particular, we have to decide that we put income here, and then we have to decide on the test condition. Especially with continuous variables, this is important. But here too, categorical variables, you have to decide to group certain categories or not. Okay. All right, let's go back. There's a third condition that sometimes we have to look at. Do we use a multi-way split? Okay. In the case of the income, for instance, we could split it lower than 80K, between 80 and 100K, or more than 100K. That would be a multi-way split. Okay. Not all trees have this. And then we need to have a stop for the decision tree splitting procedure, because otherwise your tree might become infinitely big. Okay. So you could do early termination if you want for some reason to keep your tree small. Sometimes a smaller tree, even though it's less accurate, it's more useful because you can interpret it better. Or you could use a splitting procedure or rule such as stop splitting if all the records belong to the same class or have identical attribute values. Okay. Right, so how would we split? In case of a multi-way split, we use as many partitions as distinct values, or as we saw in the example, we can group certain values. Okay. And we need to decide which to group then as well. Okay. So how do we go about determining this best split? Let's take this example where we're predicting class C0 or C1. I think this might be income class, and it's based on shirt size, car type, gender, and customer ID. Okay. Before splitting, we have 10 records of class 0 and 10 records of class 1. Okay. We actually don't really know what the class is here. Doesn't matter so much. So we could split based on, this is the root, right? Root node we're deciding. We could use either gender, car type, or shirt, or customer ID, shirt size as well. It's not in the example here. And we need to determine how to best split them. So in case we choose gender as a split, gender, male or female, right? It's translated into yes or no, but most likely it'll be female or male. If we do a gender split, then in each of the child nodes, we will have a number of instances belonging to class 0 or class 1. Okay, and in this case, with gender, no, can only guess what that one is. Male, probably. We see that there's 4 instances of class 4 and 6 of class 1. Okay. If we were to choose car type as our split attribute, then we can do the same thing. Imagine here that we're just splitting each category into a child node. This is a strategy that you can determine, really. In this case, we see that for this family car types, we have one class 0 and one class 3. for sports, we have only class 8. That's a child node. That's basically an end node then. And for luxury, we have 1 of class 0 and 7 of class 1. If we were to split on customer ID, interestingly, of course, we get all leaf nodes because there's only one customer with a certain ID. So you know the class. This would definitely be overfitting. Probably not what you want. So how do we choose the best of these options? In a greedy approach, like Hunt's algorithm, we choose nodes with a purer, homogeneous class distribution. What does this mean? This means we need a measure of impurity, so we can select the most pure nodes. Okay. In the example below, we see that if we'd have an equal class distribution in our child nodes, we would say there's a high degree of impurity, because it's not purely of one class, it's a mix. If we have something like 9,1, we would call it a low degree of impurity, because we're almost certain most of the instances belong to one class. Okay. How do we measure node impurity? We have 3 different options, for instance. I'm sure there's more, but these are the 3 main ones. Entropy, something called the Gini index, and misclassification error. Okay. So we'll go into detail on how to calculate these in a little bit. So what do? We calculate whatever measure we're using. We're going to calculate the impurity before doing the split and after the split. And then we're going to choose the test condition or the feature that produces the highest gain or the lowest impurity measure, which is the same, after splitting. Okay? So in the previous example, we will calculate the impurity of doing a split on each of the attributes, and then choose the one with the lowest impurity based on our chosen measure after splitting. Okay. Notice that, of course, if we do a split, we have impurity, class 1, class 0, class 1. We have 3 impurities. So we're going to do the weighted impurity of each of the children. Okay, so the impurity of these 3 things are going to be weighted. Okay. So what we call a gain is basically the impurity measure before splitting minus the impurity after splitting. Okay, let's look at an example. We have class 0 and class 1. And the number of nodes and the number of instances in these classes are just indicated by a code, and 0, 0 and 0, 1. And if we try do a test split on attribute A, and we try do a test split on attribute B, then it would split into nodes because it seems that they're binary features. And for each of these nodes, we can again calculate how many instances are in the respective classes. Okay. Then, from the original data, we can calculate the impurity before splitting, and using all this, known the number of instances per class, per node for each type of split, which we refer to as M, M11, M12. These will be numbers. So M1 would be the total impurity of, this is weighted. The total impurity of our first type of split, and M2 would be the total impurity of our second split that we try. From all this, we can actually get the gain, and now we need to decide if we split based on A or split based on B. And in fact, we do this by calculating the gain. The gain will be P minus either M1 or P minus M2. Easy. Now, how do we actually calculate M1 and P? Depending on which metric that you use. In case of using entropy, right, you calculate using the following formula. You probably come across this in either a machine learning class or maybe a statistics class. It's a very often used formula, and it basically captures the amount of entropy non-order, let's say, in your data. Entropy actually comes from physics, from fluidics, where entropy is the amount of movement in the atoms. Okay. So, what do? We do minus the summarized overall nodes probability of getting J given T, multiplied by the logarithm of this probability. Okay. I think this will become more clear if we look at a little example. Okay. So in this case, J given T, the probability of J given T is the relative frequency of a class J at node T. Okay. So J is the classes, like we had C0 and C1, so that in this case would be referred to as a Cj. And node T will refer to which node that you choose. So in case we had A or B as attribute in the slide before, so this would be referred to as T. Okay. Hope that makes sense. So notice that entropy-based computation are very similar to the Gini index computations, what we will see a few slides from now. Okay. So the maximum log NC is when all records are equally distributed among all classes, implying the least information. So we get the maximum entropy value when we have something like C0 equals 10 and C1 equals 10. There's no information here. You have 50% chance of being either class. If you have a minimum value, 0, then that means we have the highest amount of information. It could be something like, example of 20, C0 is 20 and C1 equals 0. Then you know all the information that all instances belong to class 0. Okay. So let's look at an example. Okay, let's calculate the probability that we have class 1 and the probability that we have class 2. In this case, 0 out of 6 are class 1 and 6 out of 6 are class 2. Okay, these represent our P, J given T. Okay, because we know that we are at node T. So then we just fill this in the formula, and we can see that the summation of minus log the probability here, 0 log 0 and 1 log 1. Okay, summarized, equals to 0. The same thing happens for the second node, where we have 1/6 and 5/6. We fill it in again here. Okay. Notice that we take a logarithm with base 2. So that means that actually what we have here is information expressed in bits. So if you want to read it correctly, it's actually 0.65 bits. Okay. That totally on the side. So if we have information gain, then that basically is our entropy of our prior to the split minus the weighted entropy over all partitions of our split. Okay, partitions being child nodes here. I should have put child nodes. And one is the number of records in partition I. So that means this term is introduced here as a weighting term. Weighing term, not weighting term. Right, so the gain really measures how much reduction there is in entropy because of a certain split. And then you can choose the split that achieves most reduction or maximizes your gain. This is how we do it in the C4.5 and ID3 decision tree algorithms. Okay. There is a disadvantage to this. Okay. There is a bias towards attributes with large number of values. Okay. Because in this case, large trees with many branches are preferred. For instance, in the case of the ID attribute, remember the customer ID where we had like a huge split? This would be preferred with this kind of approach. Okay. So that's why in C4.5 they actually use this, but they adjust it with information gain. Right, so we can split based on gain ratio. If we split based on gain ratio, we penalize the large number of small partitions. So this is exactly what we might get with the previous metric, the many customer IDs. Now we can use the gain ratio. So what do? We have our gain split that we had calculated before. And this really is divided by split info, and split info gives you some information about the number of records, number of records in the partition I divided by the total number of records, and it will actually make the gain smaller if there is a high ratio of this. Okay. I think this will become most clear when we do an example. We have an example here of the splits and how much each row would be a different type of split. And A1, A2 here are the categories or the classes, and the numbers in the table give us how many instances belong to that class. Okay. Now let's calculate, let's say, the second row. According to the formula, we can say we have minus 16 divided by 32, which is n, times log 2 of the same ratio, minus 16, again the same term, log 2, 16, of 32. And that's it. Which we can minus log 2 of 0.5, and it equals to 1. All right. So we can see here that if a lot of information, if we get a lot of nodes, a lot of child nodes, our split info becomes bigger. So if we were to go to a situation whereby we would have, in this case, 32 different attributes, this would get very, very large, and it will penalize our information gain. Okay. So that's what it aims to do. All right, other measures of impurity. I mentioned Gini, which is quite related to entropy. And Gini has the following formula. Basically forgets the logarithm, but just summarizes the squared of this probability. Okay. Again, Pj is a relative, Pj given t is a relative frequency of class J at node t. We can also use classification error at node t with classes I again. So in this case, the classification error is conceived as 1 minus the maximum probability of pi given t. Let's look at examples. The Gini coefficient is calculated. Let's take the second one in the table. We again just calculate our pi given t or j given t here. And we just take 1 minus this term to the power of 2. And we do that for every of the classes. So we get this total. This was for the second class. It's quite easy to calculate. Okay. And Gini coefficient, again, it will give us the highest purity, so the lowest measure of impurity, if there's clear which classes everything belongs to. Computing the error, okay. Again, I'm looking at the second example. We calculate our P, it's called I here, but it's really J. We count these two terms, and then we have 1 minus the maximum value of either this or that, which in this case is 5/6, and it brings us to 1/6. Okay. Again, here the difference is a little bit lower, I'd say, but as usual, it has the lowest measure of impurity for 0,6 clear, which class we belong to, and here will be a little bit less clear, so more impurity. Okay. So remember, these are actually the individual impurity measures like M1, M2, M3 from a few slides back, and they will be weighted depending on how many instances they contain. Okay. Now, if you were to compare all of these impurity measures, you see something like this. Here we have our P, J given T on the x-axis, and we have the actual entropy value on the y-axis, entropy, Gini or misclassification error, whatever, impurity value on the y-axis. And here you clearly see that entropy has a much stronger reaction. Okay, we saw this in the examples that we calculated as well. Misclassification error is sort of the most gradual one. Gini is also pretty gradual, but entropy has a much more, a big reaction. So it's really up to you which measure would be best for your problem. Okay. So there are some practical issues when building decision trees. Decision trees are built by greedy search algorithms, guided by some heuristics that measure impurity. In real-world applications, we should also consider the fact that we have continuous attributes. How do we split a salary? There might be missing values that need some pre-processing. The computational efficiency of decision trees can be low, sorry. And you could have overfitted trees like based on customer ID. So these are some issues that we do need to be aware of. This should be splitting based on continuous attributes in many cases. So there's different ways of handling this. One way would be to discretize the original continuous variable to form an ordinal categorical value. So basically, you bucket it, you bin it. Mm-hmm. You could do it once at the beginning, but even there are some decision trees that do this dynamically, so to best fit the decision tree. Okay, but that one is computationally quite expensive. Then you can just make a binary decision. Okay, consider all possible splits and then choose the best one. Also computationally a bit more intensive. I have already mentioned that you can overfit using decision trees. When a tree becomes too large and it's going to, let's say, have too many rules, basically taking into account all of the attributes and learning individual customers rather than general rules, then it is going to be overfitting. Okay, and then the error rate is going to go up. How is that possible? Because the error rate is calculated on the evaluation set or the test set, not the training set. So you will see the training set loss go down a lot, but if you test the test set loss, it will go up. So it's always important to use a separate test set. Okay. Just as there's overfitting, there's also underfitting. So underfitting is when your model is too simple, and then you'd basically have both your test set goes like this, but also your training set has a large error. Okay. How to address overfitting, Usually, we have stopped the algorithm when all instances belong to the same class or when all the attributes values are the same, but we can do early stopping, and early stopping will prevent overfitting. It means stop if the number of instances, for instance, is less than some user specified threshold, okay, 5 or 10 records per node. Let's say we can be, usually you'd want to go for 100% of the same class per node per leaf, but maybe you are happy if 1 out of 10 belongs to another class, right? So you're like 90% of your instances are correctly classified in the leaves. One option. You can also stop if the class distribution of the instances are independent of the available attributes. This is a bit more complicated, and you can use a chi-square test to do this. You could stop if splitting the current node improves the impurity measure below a given threshold. So you need to make a certain advance, otherwise you'll just stop. In case you're wondering about this chi-square, so basically you stop growing the tree when there's no statistically significant association between any attribute and the class at a particular node. Okay. So other things we can do to address overfitting. Post-pruning. You grow the tree in its entirety, so you have a huge tree that's way too big, and then you're going to start to trim the nodes of the decision tree in a bottom-up fashion. You can do something which is called reduced error pruning. Okay, reduced error pruning considers each node for pruning. So pruning is really removing a subtree at that node and make it a leaf and assign the most common class at that node. Okay. So a node is removed if the resulting tree performs no worse than the original on the validation test set. So it removes coincidences and errors. Nodes are removed iteratively, choosing the node whose removal most increases the decision tree accuracy on the graph. So this kind of pruning usually continues until further pruning is harmful, okay, by checking with the validation and test data set. This is usually an effective approach if there's a lot of data available. So you can also use a data set not used in the training set, which we refer to as a pruning set. So you can use that to make sure that your performance stays accurate while you're removing subtrees. Okay. If the test error in the pruning set improves after trimming, then prune the tree. Improves or continues to be the same, I'd say. So we can do post-pruning using two techniques: subtree replacement and subtree raising. Oops, let's look at this in detail. Subtree replacement. Okay, how do we go about this? We split the data into training and validation set. Do this until further pruning is harmful. The next steps: evaluate the impact on the evaluation set of pruning each possible node and select the node whose removal most increases the validation set accuracy. So you're actually trying to increase the accuracy or keep it the same. So what are you going to do? You're going to select a subtree like this and replace it by a leaf node. Okay, and then the leaf in this case would just become the label that is most in this might be bad, depending on how many instances there are in the child nodes here. Then we can do subtree raising. What is subtree raising? We have a subtree like this. And we are basically going to move the instances to surrounding nodes. Okay, so we're really deleting this node and then redistributing these to other nodes. Okay, it is slower than subtree replacement though. Right. So how does all this work in the algorithms that I mentioned earlier? R3D uses Hunt's algorithm with information gain criterion and gain ratio. Remember gain ratio to avoid many subtrees. subtrees, many, a huge amount of splits, right? C4.5 improves on this I3D, but it needs the entire data to fit into memory. I could see that as an issue for big data. It handles missing attributes and continuous attributes, so it has strategies for splitting, and it performs post-tree pruning. Okay, there's a successor to this, C5.0. There's CART that builds multivariate decision trees, and it supports regression even. Okay, so you can use this not just for classification, but also for regression problems. So, in sum, decision tree-based classification. It's inexpensive usually to conduct. It's very fast at classifying or inferring new data. It's easy to interpret, which can be a huge plus. It's robust to noise, especially when you do some of these overfitting methods, and it can easily handle redundant or irrelevant attributes. Okay. Some of the disadvantages, the space can be exponentially large, so greedy approaches can't often find the best tree because we're using heuristic search methods here to train our data, and it doesn't take into account interactions between data. Also interesting. Each decision boundary involves one single attribute. So it wouldn't say if this and this, then this. It doesn't really do that. Okay, I think this is a nice overview. Personally, decision trees are one of the first models I just run to have a look at the data. It helps me see what the data does and which attributes might be important. But then in the end, usually I'll end up taking another model, an ensemble method, SVM or logistic regression or neural network that'll typically perform better. Okay, so that brings us to our second classification algorithm, rule-based methods. The good thing is it's practically the same as decision trees, but it's written out horizontally. Let's have a look at an example. Here's a data set. They're animals, and we're trying to predict if they're mammals, reptiles, fishes, etc. This is an example rule set. Rule 1 gives birth, no, can fly, yes, then it is bird. Okay. We have the union operator here. Gives birth, no, and lives in water, yes, then it's fishes. So we have a bunch of rules. They could equally have been written out as a decision tree, really. Okay. So, and we can go over each of the attributes and then we find our rules. Note that not all of the attributes need to appear in a rule. In this case, we only look at birth and live in water. Okay. So, applications of rule and covering. So we say that the rule R covers an instance X if the attributes of the instance satisfy the conditions of the rule. Okay. In the case here, we can say that rule 1 covers hawk, class is bird, this first example in the table. Because if we're looking at classifying hawk, we can say, does it give birth? No. Can it fly? Yes. Then it is a bird. This we can derive from rule 1. So rule 1 covers the instance hawk. Grizzly bear. What rule covers grizzly bear? I think that rule 3 covers grizzly bear because the blood type gives birth, yes. Blood type is warm, yes. So it is a mammal. So this is the concept of covering. So from rules to decision trees. If you consider a rule set as follows, A equals 1 and B equals 1, then it's class Y. C equals 1 and D equals 1, class is Y also. Notice you can have multiple rules for one class. Otherwise, class is n. How can we represent this in a decision tree? To do a decision tree, we need a common attribute, which is the root of our node. So we can rewrite these rules in the following sense. And we made sure that the attribute A is in all of the rules. This allows us to unfold the tree. It is more verbose, but it will form a nice graphical representation. Okay. So, if you're building classification rules, you can use two types of methods. A direct method, which directly extract rules from the data, like Ripper holds 1R, or you could use indirect methods, which extract rules from classification models. Like if you have a C4.5 decision tree, you can get the rules from there. So let's have a look at one of these direct methods, which is sequential covering. We start with a training set E, and we're going to be extracting rules one class at a time. Okay. For each class C, initialize a set S with E, the training set. While this subset, which is still E in the first step, contains instances in class C, learn one rule R for class C. Remove then all the training records covered, remember the concept of covering, by rule R. Now S is smaller and does not contain the instances covered by this new rule. And we repeat this process over and over again. Okay. And that's it basically. You do this for every class. Another direct method is Ripper, which stands for repeated incremental pruning to reduce error. For a two-class problem, meaning we only have two categories to classify into, we can choose one of the classes as the positive class and the other as the negative class. Then we proceed to learn the rules for the positive class, and the negative class will be default. So much like the example that we saw before, we actually have rules only for one class. Everything that doesn't fall or is covered by those rules will be default class. In case of a multi-class problem, we proceed to order the classes according to the increasing class prevalence, or basically the prior distribution of the classes. Okay. When we look at the fraction of instances that belong to a particular class and classify them small to large, we start by learning the rule set for the smallest class first, then treat all the rest as a negative class. We proceed to repeat this with the next smallest, so slightly larger class, meaning the class with a slightly bigger class prevalence. Okay, to proceed that as the positive class. So, still treating the rest as a negative class, and we repeat this until everything is covered. In Ripper, we start from an empty rule and we add conjuncts, sort of terms, to this rule as long as they improve the information gain. Ripper uses FOIL. Ripper uses FOIL as a metric for information gain. We're not going to go into detail for that particular one. So we stop when a rule no longer covers negative examples. Okay. So we prune the rule set as well immediately after, using reduced error pruning. The measure we use for pruning W of our rule is P minus n over P plus n. So whereby P is the number of positive examples covered by the rule in the validation set, or the pruning set, however you call it, and n is the number of negative examples covered by the rule in the validation set. Okay. So pruning starts from the last added test to the rule. So meaning, you have all these conjuncts in your rule, this and this and this, or this, and the last of these conjuncts is where the pruning starts. So it may create rules that cover some negative examples, thus actually lowering the accuracy. And Ripper actually also implements a global optimization or pruning strategy after all of the learning is done. All right. So we use the sequential covering algorithm. That means we start from our whole set of positive examples for which we need to learn a rule. When we have a rule, we eliminate both the positive and negative samples covered by this rule from the dataset, and we continue with a smaller dataset. Okay, so each time we add a rule to the set, we remove the covered instances from our dataset. Okay, so our dataset becomes smaller and smaller, and thus it becomes easier to learn rules. So we also compute description lengths, which is sort of the length of the rule set in terms of characters almost, and we stop adding new rules whenever this description length is d bits longer than the smallest description length obtained so far. Okay, so this is just a stopping criteria. Let's have a look at C4.5. This is a decision tree, rules versus Ripper rules. This is the example from earlier, whereby we are classifying different animal types. Sorry. And from this decision tree, we can write out this decision tree as a rule set. Notice that we have the root node present in all of the nodes. Compare this to Ripper, then we have a slightly different rule set, still having similar accuracy. But the rules sort of look different because they don't have a root node in common and they can basically have as many attributes as they want. Okay. Whereas there's a certain order to the decision tree rule sets. Advantages of rule sets are that they're highly expressive, easy to interpret. So in some cases, it's really necessary to be able to interpret your data. The law might require you to say why you're refusing credit to certain customers, or you might just want it for your own validation internally. If your management requires you to have interpretable rules of why you make decisions. They're quick and easy to generate. We can classify new instances rapidly. Inference is very quickly. And it has a performance comparable to decision trees. We can easily handle missing values and numerical attributes because we don't have to go through this whole node root thing like in decision trees. All right. Let's have a look at k nearest neighbor. A very simple classifier, really. The thing with k nearest neighbor is it's going to plot, no, not really plot, it's going to take all of the instances in the training set in its memory, which might create a problem on its own. And then for any new instance x here, it's going to compute, in the case of one nearest neighbor, it's going to look at which one is closest in terms of some distance metric, like Euclidean distance. So in this case, the closest element is negative, so we classify this as negative. Easy. In the case of two nearest neighbors, we're expanding our circle and we're looking at the two nearest instances. Since we have both classes equally represented, we are forced to expand this to three nearest neighbors, in which case we will revert to positive class prediction. Now, I already mentioned it. We have to compute the Euclidean distance with all pairs, right? This will take a long time to compute, and you need to keep everything in your memory. So, while it is a good algorithm, it can actually be very computationally expensive. Whenever you use k nearest neighbor, it is important to make a good decision on k. In fact, for any good data science algorithm, you're going to need to tweak your parameters. Whether you're using a decision tree and you need to decide on the number of nodes, pruning criteria, impurity measure, or you're making SVM and you have your cost factor, you have neural network and you have your hyperparameters you need to optimize. If you were just to compare some default algorithm with another default algorithm, it would not perform well. Okay. Take the case of k nearest neighbors. Here we are plotting different values for k on the x-axis, and then together with their validation error. You see that in case we just arbitrarily decided k to be 2, we'd have a very high validation error. On the other hand, if we decide k to be 10, we actually have a pretty good performance. This is why it's important to have a validation set that you can use to tweak your hyperparameters. So remember, you have your training data set, you have a test set separate to evaluate your algorithm, but you keep part of the training data that you reserve to do tweaks like deciding on k. We'll be looking at something called grid search as well to do optimization of different parameter settings, and you might find this useful for other algorithms. We'll be having a look at this in the SVM section. So k nearest neighbor, straightforward, simple. It is very sensitive to the value of k, so be careful to that. If it's too, oh gosh, sorry. It is very sensitive to the value of k, so if it's too small, it becomes overly sensitive to noise and outliers, right? Imagine if you're only looking at one neighbor in the example here, right? And this one is an outlier, you'd happen to choose it. If you have a larger k, you're less sensitive to outliers in that case. If it's too large, your neighbors might include points from other classes and you're not able to make a firm class boundary. So yeah, try to optimize the value of k. It is computationally expensive. We need to compute all the distances and we need the memory to store all the data points. So if I send you a neural network model, it's a small file because it just needs some weights for my nodes, right? If I send you a k nearest neighbor pre-trained model, well, what is there to train for KNN, right? That means I'm just sending you my data set. And as you know, data sets can be really big. All right, here's one of my favorites, logistic regression, because it's simply so simple. We have an example here, binary classification, only one attribute, x or x1, let's say. And class label, does it have this person have insurance? Yes or no? 0 or 1. Easy. Let's plot this data. If we plot the data, we see that we have age, the x1 feature, and we have insurance or class label y. Now, how do we separate this data based on the age attribute? Well, if we fit a linear regression model, it would look something like this. Linear regression learns a linear line, and based on that line, we have a threshold which is typically 0.5. Based on that threshold, we can separate our classes. Okay. Now all of these are considered to be class 1. All of these are considered to be class 0. Simple model, easy to learn. However, we have quite a bit of misclassification happening. Okay. So, how can we do better? What if, in fact, actually, let's change our example a little bit. Let's say our data is shifted a little bit more to the left, and we have the same sort of classification happening, but now our linear line can't really separate this. So we need another solution. And the other solution would be a logistic regression. In this case, a logistic regression learns a sigmoid function, and this sigmoid function fits our data as well as possible. We again have a threshold value, typically 0.5, but it could in theory be different. Based on the threshold value, we now draw another line that classifies these points that were misclassified in our linear model in the correct class. Granted, there are still some outliers that this model is not able to detect, but it is much more flexible than a linear model. How does this work? It is a simple sigmoid function. This is a standard sigmoid equation. In the linear model, we had the equation on the left, whereby x really is a vector. You have to look at x as a vector of the different attributes. We only have one x here, but when does that ever happen? So if you read x, really think of it as many x's. And the same with m, of course. We have a coefficient for each of these x's, etc. You've seen this in your statistics class, no doubt. Now this same equation here, let's call it a, is actually inserted here in the logistic function. So it's very easy to memorize. You have 1 over 1 plus e minus a. There we go. Right, this threshold value, is it always 0.5? No. It's up to you to choose a good value based on the confusion matrix. And as you know from the first lecture, confusion matrix gives you a nice overview of your true positives, false negatives, and true negatives. And you want to sort of optimize the number that is on the diagonal here, right? So this table usually actually is much larger than 2 by 2. It can be pretty huge, depending on how many classes you have. All right, so there's a concept I want to talk a little bit about, which is logit. So in logistic regression, and take here the case that we have multiple variables, as I mentioned, your x really is a vector. So that means instead of taking mx plus b, what you really have is the summation of mixi plus b. Right, over the whole data set I. Xi here, the number of input features, mi, the coefficients that you learn in your linear model, or logistic regression model, if it's in this case. So, how do you make class decisions? How do you infer class? The probability that a new entry is of class 1 is simply the logistic regression equation. Okay. The probability that its class is 0 would be 1 minus this probability. Okay. This brings us to when to decide which probability to use. So if we use a 0.5 threshold, we can actually calculate the odds that class is 1 over class is 0. Okay. It gives us the odds that something is class 1. And if we actually calculate that, we can, if you fill in the equations here, we can actually derive that to this equation. I'll do it on the next slide, in fact. Now, what we call logit is basically the logarithm of the odds. And what's so nice about it is if we derive this, if we take the logarithm of this function, it removes the e basically, and we just get a nice linear regression equation again. So this means that the logarithm of the odds can just be represented as a simple linear regression. And if we have data like above, where we have the class probabilities, and we have a sigmoid, we could write it in a different way, whereby we get something like a linear equation, the logit, and logit will give you the logarithm of the probability that this belongs to a certain, this is not xi, this is x, belongs to a certain class. Okay, so it's very quick and easy to make inference. You just need a linear equation. Okay, so how do we get actually to this equation here? Let's take the odds. Okay, The odds are the probability of it being class 1 over the probability of it being, that's odds, p class 1 over p class 0. We fill in this, which is the equation for sigmoid, the sigmoid function above from the logistic regression, whereby z is just this linear regression. We know basically odds are p over 1 minus p, right? And that is what this equation says. Now, if we sort of do some mathematical reduction here, we multiply this bottom term by this term, and then we can put it on the same denominator. We can strike through some things. Then we multiply both by this term, falls away again. Then that just leaves 1 over e minus z, which again is just e over z. If we take the logarithm of e over z, we get z, which is exactly the logit. So logit function here is the logarithm of p over 1 minus p, because we can do this because we have a binary classification, right? Okay. Right. If we have multi-class classification, that means that we need to learn a regression model for each class, and then just choose the class with the highest prediction probability. Okay. So we have 3-class problem. We need to train 3 logistic regression models. Okay. The disadvantage here is that we cannot make dependent predictions. All the predictions are independent. For instance, if cars are expensive and a car is detected, the model for expensive will not know that the car is detected because that probability is made by another model. Okay. So it's independent. Okay, that brings us by an exciting classification model, support vector machines that were very popular in the early 2000s. SVM support vector machines. We can also use it for regression. In that case, it becomes SVR, support vector regression. It's a classifier derived from statistical learning theory by Vapnik. So it became famous because it was able to perform as well as neural networks back then on the handwriting recognition tasks. You know, the famous MNIST, which is like the hello world of machine learning. So I'm sure you've come across it. If not, we might in our CNN lesson. So SVMs are widely used, object detection, text recognition, biometrics, etc. I use it for hit prediction, composer classification, speaker identification, emotion prediction. I've used it in many cases. It's been the best performing model. However, sometimes it is combined with something like neural networks, transfer learning, to handle the feature extraction part. So we can use convolutional neural networks with all the filters and effects to learn meaningful features from our images and then feed those features into an SVM. So sometimes these combined models work very well. So to understand SVMs, we need to talk a little bit about margins and confidence. Okay. Suppose we have a simple classification. Okay. In this case, the axes are features, and we have a linear classifier. In this case, we can define geometric margins as the distance of an instance from the separation line. Okay. So, in SVM, it's all about optimal margins. So, suppose, what SVM does is it transforms our features into a new space where we can do linear classification. Okay. That's the basic principle. And it uses a kernel function to transform us into the features into a new linear space. Okay. A space where linear classification is possible. So instead of putting the features on the axis here, I put phi1 of x and phi2 of x, which are the transformations of the features after applying the kernel function. Okay. And once we've done this, we can calculate linear equations that are class separation boundaries. This is all multidimensional, so we're actually not talking about a straight line, we're talking about a hyperplane. And the hyperplane here, it's a normal equation of a line, except instead of x, we use phi of x, the transformed x, and we use weights or coordinates that are transposed here because they're considered matrix operations in a multidimensional space, which is not so important. Okay. What a SVM does. SVM calculates the distance between the closest element of a class and the boundary. In this case, plus here would be the closest, and the x here would be the closest. Okay. And then it's this distance here is what we call the support vectors. Okay, this is where the name comes from. So we draw, and SVM learns these two lines here, which form the margin between the decision boundary, and the closest element. Okay, and when we're training an SVM, it is all about optimizing this distance. Maximizing this distance is what we want. Okay, so it's pretty simple if you look at it this way, except it's actually pretty hard to optimize because we're using hardcore optimization techniques. Okay. So giving a training set of n data points consisting of xi's, the input variables, and yi's, the labels, with input data belonging to the real domain, and binary classification labels -1 and +1, the SVM classifier fulfills the following conditions. Okay. So these two lines around the decision boundary need to be +1 and -1. Okay. Larger than +1 or smaller than -1. That's how they have a minimum distance. Okay. Which basically equates to saying that multiplied by the class label xi, which is -1 or +1, they need to be larger than 1. Okay. So it's important here to consider the phi transform, the new variables phi of x. Phi is the transformed input variable. And let's again think about why we need this. Sometimes we have data that is just not separable by a linear line. I cannot draw a line to separate my blue from my red dots, so it's a bit hard to see. So instead of my line, I'm sorry, my line is still there, we need to basically transform our data into some hyperdimensional space where we can use a line to separate our classes. And of course it rotates, so I totally did not put my line correctly. But you see now, using a straight plane, we can cut off and make a neat separation. So to do this, get this new variable, what we need is a kernel to do the transformation. So these new features that we get after applying phi is basically the input features fed through a nonlinear function that maps the input space to a high and possibly infinite multidimensional feature space. Okay, that sounds complicated. It just means that we have x1, x2, x3, and it can be a really high number of x's. Okay, right. So in this case, instead of thinking of this as a line, we need to see this multidimensional because x is a vector. And because it is multidimensional, it becomes a hyperplane. Okay. What we want to do is we want to maximize the margin between the two classes, which equates to minimizing the weights in the equations. So this is optional. I'm not going to ask details on the mathematics here because this is just a really brief glance into it. To properly explain this, I'll need to go into much more details and mathematics, which isn't necessarily the objective of this class. You'll see this in machine learning courses. So the convex optimization that we use to train the SVM is defined as follows. We are minimizing the margin, which is expressed here, and we have a second term that basically does regularization. Okay. For this regularization, we include some slack variables that are needed to allow misclassifications in the set of inequalities. This prevents overfitting, for instance. Now, this cost factor C, actually, or the regularization coefficient, often people refer to it as a cost factor, is actually set by you. You choose this value, so you need to tune this value because the performance of the SVM is highly dependent on C. Okay. All right. So that leads eventually to the following classifier, whereby you have the original input run through a kernel function K. We have some Lagrange multipliers that are determined during optimization, and we feed it through the sine function. How we get to this equation isn't so important. It involves some complex mathematics. Okay. Important thing here is the kernel functions, which are basically a particular phi of xt transposed and multiplied by phi of x. Now, I don't want to go into details of a Mercer theorem, which is a mathematical theorem that talks about representation of a symmetric positive definite function on a square as a sum of convergent sequence of product functions. So I don't want to go into why we are using this, but what is important is to know that you can use different types of kernel functions, each of which resulting in a different type of projection of your data. And two popular ones here are the polynomial kernel and the RBF kernel. RBF, radial basis function. Okay. Again, in these kernel equations, we have a few constants that we need to set. So we have a lot of hyperparameters here to tune, and how we set them will determine our performance. Note that because of our prediction function basically does not give us any insight into how predictions are made, we cannot relate it back to X and Y. That means that SVM is a black box model, and it'll work, most likely you'll get a better accuracy than decision trees, but you won't be able to explain how you get your result. Back to the hyperparameter tuning. We use an algorithm called grid search. We'll demonstrate this in the labs too. I kind of like grid search because it's so, it's pretty quick for optimization, and it's very useful. Imagine we want to optimize our gamma from our kernel function and our our C function. Okay, so what we do is we form a grid. We tell the grid search we want to try for G, we want to try this, this, and this value. For C, we want to try this, this, and this value. It'll start random on the grid. It'll do twofold cross-validation for all of the points it can reach from this grid. And for the best point, does tenfold cross-validation. Then, from that point, it repeats itself and looks for the best point. So it sort of forms a path until it reaches good parameters. Okay, it's fast because you don't do tenfold cross-validation everywhere, you do twofold, meaning it's 5 times as fast. Okay. If no better pair is found or the border is reached, then it stops. Okay. All right, that brings us with the Bayesian methods. In particular, I want to focus on naive Bayes. Now, but let's first recap Bayes' theorem a little bit. So Bayes' theorem gives us mathematical formulas to calculate conditional probabilities. For instance, the probability of A given B can be expressed as the joint probability of A and B occurring divided by the prior probability of B. Okay. The same for the reverse. Okay. Now let's have a look at an example. Okay, because formulas and examples can sometimes be hard to relate. So in this table we have data for teacher, student, and together with their gender. So we see basically Bayes is all about counting, right? Counting instances. In this case, they've counted how many teachers are female, how many teachers are male. This must not be ISTD because we're only 2, I think. And if you fill that in the conditional probability of a teacher, given that we're looking for male, we can express it as this. What's the probability of a teacher and male, of being a teacher and male? That would be 12 divided by the prior condition of the probability of being male. Probability of being male would be 60. So it would be 20% chance that you're a teacher given that you're male. Okay. Right. So we can rewrite this a little bit. So because we can use the probability of the union of A and B to the probability of B given A times the probability of A. Okay. Why do we want to do that? Because then we can rewrite this as follows. So we can say that the conditional probability of A given B equals a conditional probability of B given A times the prior of A divided by the prior of B. Okay. So this is what they refer to as Bayes' theorem. Okay. So it basically describes the probability of an event based on prior knowledge of conditions that might be related to the event. Now let's move on to naive Bayes. Naive Bayes assumes that all of the features, the input features x1, x2, etc., are independent. Right? So we often, sometimes in the examples, I'll use x. In fact, x typically would be a vector consisting of x1, x2, x3, etc. Right? Because in the real world, we have multiple multiple input features. Okay. So if we look at Bayes' theorem, and we now assume that the features are independent, we can write it as follows. The conditional probability of A being k given all of our input features equals the probability of feature 1 given A equals k times feature 2 given A is k, etc. for all the features until n times a prior probability of A over the prior probabilities for each individual x multiplied, input feature multiplied. Okay. So basically, the probability of certain outcome given the evidence being the x's or input features, equals the probability of likelihood of evidence times the prior divided by the probability of the evidence. Okay. Let's look at an example again. We have a data set here with probabilities. Right, so we have fruits, orange, banana, other, and we have, is it long, is it sweet, is it yellow, etc. It's Bayes, so we need counts. So we aggregate this into a count table, and we see that for different fruits, so for instance, banana appears twice here, it'll appear many, many times. In fact, probably 400 times. For each of these, they're aggregated into one row here. For banana, we see 400 times it occurs as long. It seems to be medium sweet, yellow, all the time. In total of 500 counts of banana. Okay. So this is how we made this count table again. The objective: predict if a given fruit is banana, orange, or other when only 3 features are known: long, sweet, and yellow. Okay. Step 1, compute the prior probabilities for each class of fruit for each of our yi. If the probability of it being banana is basically 500 divided by the total number of fruits, orange 300 divided by 1000, and other 200 divided by 1000. Intuitively makes a lot of sense. Step 2, compute the probability of evidence that goes into the denominator. This is the priors of the x variables, of the evidence. Okay, the probabilities of the evidence. The probability of it being long, 500 over a total of 1000. Sweet, 650 over 1000. Yellow, 800 over 1000. Again, pretty intuitive. These are just non-conditional probabilities. Then, let's compute the probability of the evidence that goes into the numerator. Okay, so these are the conditional probabilities. Okay, x1, it being long, given that it's a banana, is 400 over 500. Being sweet, given that it's a banana, 300 over, oops, sorry, this is my bad here. Need to refer back to here. Sweet, given that it is a banana, or yellow, given that it is a banana. This gives us the conditional likelihood of evidences given the fruit or the class. So it is the overall probability of the likelihood of evidence for banana. We will actually be multiplying all of these in the numerator. Okay. So step 4, fill in everything. Substitute all of the 3 equations in the naive Bayes formula. So, in case we're wondering, is it a banana? This is the example we did. You can do it for the other fruits as well, if you calculate it yourself. The probability of it being banana, given the evidence that it's long, sweet, and yellow, we fill it in, and basically, let's do it here. We have on the previous slide, we've calculated that these are the 3 probabilities multiplied, 0.4504. So we have 0.504 times the prior probability. Remember, we multiply, let's take the naive Bayes. So we need this prior probability of it being a banana. And then we calculated that as well. Sorry, here. That would be 0.5. So we fill this in as well. Given that it is long, sweet, and yellow, here would be these multiplied. Let's quickly do that. Do I remember correctly? Yes. Almost. Right. So why didn't I do this, add this term in the formula? Because the probability for all of these would be the same. The prior probability of the evidence in the denominator is the same for all of the categories. So it really doesn't matter so much if our goal is to compare these. Okay? All right. So give it a try and calculate the others, see if you get the same result. I probably removed the denominator for all of them. Right, so the value of P orange, long, sweet, yellow was 0 in the above equation because long given orange was 0. So when you have a model with many features, the entire probability will often go to 0 simply because one of the features probability was 0. So to avoid this, we increase the count of the variable with 0 to a small value, usually 1 in the numerator, so that the overall probability doesn't become 0. Okay. This is what we call the Laplace correction. Okay. All right, that's basically naive Bayes. It's a very simple method. And that brings us to some exciting hybrid methods, which we refer to as ensemble methods. In an ensemble method, we basically construct a set of classifiers from training data. The emphasis here is on set because we're actually creating many classifiers. So we predict the class label of the test dataset by combining the predictions made from the multiple classifiers. So if a classifier is weak on a certain aspect, we're hoping it's going to be compensated by the outputs of the other classifiers. We have many types of ensemble methods. I'll focus on 3, bagging, boosting, and stacking. Okay. Bagging focuses mainly on getting an ensemble model with less variance than its components, whereas boosting and stacking will mainly try to produce strong models less biased than their components, even if variance can also be reduced. So, bagging considers homogeneous weak learners, and it learns them independently from each other in parallel. Okay, why don't I just go over the details of each of these so that we can better understand them, and then when we come back to these definitions, you're going to better understand them. Okay. So, let's have a look at bagging. So bagging takes a set of homogeneous weak learners. What does that mean? Homogeneous, the same type of classifiers. And it just learns models independently and then combines them following some sort of deterministic averaging process. So let's say it could be a strategy, something like model 0 predicts class A, model 1 predicts class A, and then model L predicts class B. Perhaps your strategy of averaging them could be what is the most common predicted class. Okay. In this case, A, and that is your result. It could be a little bit more of an elaborate strategy. Maybe you're going to summarize all of the probabilities of A in model 0, so A for each model over I being the number of models, which is L here. So that could be another strategy, and then taking the class with the highest predicted total probability. Okay. So you have these weak learners, and then they're all following some sort of process to combine them, and you get a final prediction in the ensemble. Okay. A random forest is a special case of bagging. Random forest, as you might have heard, it's not a decision tree classifier. However, all of the homogeneous models in this classifier are decision trees. So we have different independently trained models, different trees here, which basically are combined in a simple majority voting way. So in this case, indeed, the most predicted class will be the final class. There is actually a small exception. This is a special bagging case because the random forest approach is a bagging method where deep trees, so these will all be deep trees because here we're not concerned with comprehensibility or understandable interpretable models. So each of these trees are combined to produce an output with lower variance. Okay. So they also use another trick to make the multiple fitted trees a little bit less correlated with each other. When growing each tree, instead of only sampling over the observations in the dataset to generate the bootstrap example, we also sample over features and keep only a random subset of features to build the tree. So there's some regularization happening here. Okay. So instead of training on the same bootstrap samples, the same training data set, we actually also sample over features for the different trees. How we'll have different input features. Okay. And that forms a random forest. It's a pretty simple model, and it actually performs pretty well most of the time. So what are some of the characteristics of decision trees versus random forest? Decision trees are inexpensive to construct. The results are easy to interpret, at least for small trees, but they're prone to overfitting if you're not doing pruning or early stopping. Random forests, so which combine multiple decision trees, will use different data samples, this bagging, right, and random training features. Random forest avoids overfitting due to this whole feature sampling, and they will improve the accuracy because it's an ensemble model. Okay. Boosting. In boosting, we fit models iteratively, such that the training of a model at a given step depends on the models fitted at the previous step. What does that mean? Records or instances in our dataset that are wrongly classified will have their weights increased, and records that are classified correctly will have their weights decreased. Isn't that interesting? So it's sort of depicted on the picture here, which is an example of adaptive boosting or AdaBoost. In AdaBoost, we train on a weak model, and then we have an initial setting for which we'll actually do a check to see how well it classifies, and we'll see that, for instance, this and this one instance is wrongly classified. When we're training the next model iteratively, that means that the weights of these misclassified instances are increased so that hopefully the decision boundary will actually move a little bit to include these more, okay? And hopefully combining both of these models, you'll see that there's a few new misclassifications here, but they're still correctly predicted by this model, okay? So combining these two models will actually give you correct predictions for each of the items, and by combining all these, we hoped to have a more correct final estimate. Okay, popular techniques include gradient boosting and AdaBoost. Okay. So in AdaBoost, the weights of the observations at each iteration are updated, and the weights of well-classified observations may decrease a little bit. Models that perform better will have higher weights in the final ensemble model. Okay, right. So in addition to weighing these instances, we also weigh how much these final models contribute to the final prediction. Finally, we have stacking. Stacking learns several different weak learners and combines them by training a meta model to output predictions based on the multiple predictions returned by these weak models. So this case, instead of looking at the final class, A or B, we're actually going to take the probability of A and the probability of B. And using that as input, we're going to learn another model that will output the final prediction. Okay. This does not need to be homogeneous. These can be a neural network, a different neural network, KNN, anything can be combined here. Okay, and then the final model also could be a neural network or whatever you want, SVM. Okay. Right, so that's an overview of some of the most important models in data science. Neural networks will have a whole separate class on that in 2 weeks' time. And I just want to briefly reiterate some evaluation aspects. So it is super important to have both a training set and a test set. I've mentioned this already. But we do really need to train the model on a separate data set. Otherwise, we cannot possibly correctly evaluate. Instead of just doing a split test set, training set, it is actually, we could get lucky having a test set that happens to fit well with our training set. A better strategy, a more robust strategy, more representative strategy is to use X-fold validation. Okay. in this case, what we're going to do is something like stratified sampling. Okay. In stratified sampling, we are going to split our data set into test and training sets. In this case, we're going to sample multiple training sets and test sets. Okay, and then we're just going to learn a model and test the model. Learn another model, test the model, and we do it multiple times, and then we get the average of these results. In random sampling, we just basically random sample from the data set. In stratified sampling, we maintain the proportion of class labels. Okay, what does that mean? If our training data set has 1, 2, 3, 4, 5, it's 50-50 of each class, then our training set will also have half, and our test set will have half. Does our test and training set need to have the same probability distribution of classes? This is a tricky question. Because really what you want is you want to have your training set and test set to have the same distribution of classes as your actual real life data has. Okay, because you're kind of making the problem easier if you do stratified sampling. Okay, but if it's representative of real world data, then sure, why not? Okay. So similarly, a little bit more of a structured technique is called k-fold cross-validation. Pretty robust. K-fold cross-validation splits our dataset into k folds. Here we have 5 folds, partitions here, and we take all of the folds except for one that we use for test. All of the folds, and we use one for test. And we do all possible combinations. In 10-fold cross-validations, we have 10 possible combinations. For each of these, we get results on the test set, and we average these. Now, this is a very, very robust way of testing and really honest way of testing how good our model works. Right, so we also have leave one out validation, which actually is a special case of k-fold cross-validation. Your test set is just 1. Basically, k here is the number of observations in your data set. Okay. Then you have noticed that we often have something called a validation set or a pruning set in decision trees, which is basically a development set. Okay. So part of the training data set is often used for development to help fine-tune the parameters of the model you're developing, okay, before testing it on the training set. This will greatly improve the accuracy of your final test set model without overfitting on the training data. Other ways of testing classification problems include confusion matrix, where you calculate true positives, true negatives, and these are the ones you want to optimize, against false positives and negatives. Okay, this table can become really big because there's basically a column for each of your classes. And it's a very good way to give you some insight into how your model works. Accuracy basically can be expressed in terms of this true positive and true negative, because it's basically the sum of this divided by everything. The problem here is if we have unbalanced classes, what does that mean? I have a data set, the number of entries, and let's say I have trying to predict gender, and I have females and I have males. Okay, this is not balanced. So if, let's say, I am trying to predict one of the two classes, and I'm looking at the overall accuracy, and you say it's 90%, maybe, 99% of my data set was female and 1% is male. If I'm predicting, I'm just saying it's always female, my model just says female, yes. That's all. That's my model, my whole model. The accuracy of this model will be 99%. Ha! You see how accuracy is totally you say, it's totally wiped away if you have unbalanced classes. So one of the things I want to see in your project is your dataset classes, your Ys, and how much of it is in your dataset. Because this will give me an interesting aspect or insight into this number here. Okay? Because really, accuracy without mentioning the class distribution is meaningless. What you can do instead is you can do the class specific accuracy. In this case, that means doing the true positives over the total here and the true negatives over the total here. In the case of female-male, we have the class specific accuracy of female is 99 over 99, 100%. The class specific accuracy of male is 0 over 1, so it's 0. Okay, so that tells you a lot. Okay. So if you use accuracy, take class specific accuracy. Other metrics to compensate with this is precision. So the percentage of classified items that are correct. It is true positives over true positives and false positives. So here the sum. Recall is the percentage of correct items that are classified, which is basically the class specific accuracy, as I already mentioned, TP over the sum here. Okay. Okay, so we have sensitivity is the true positive rate, basically, and we have specificity being the true negative rate. Okay, so that would be here, true negatives over the total. Okay. Right, so here's a visualization of these two. This is an image from Wikipedia. I think that really shows you how we need to interpret this. All right, so what should we optimize for? Okay, recall or precision. Basically, if you don't know and both are important to you, use the F1 score, which is basically the harmonic mean of precision and recall. Okay. Right, because between precision and recall, there's always a trade-off. If you have 100% recall, you just retrieve everything, just as in the example that we had above. Another nice way of evaluating your model is through the receiver operating curve. In this case, we vary our classification threshold. And by varying the classification threshold, which is often 0.5, we move along and form this line. This line is between the true positive rate and the false negative rate. And this diagonal basically is a random classification model. So if we're here, it's a random model. The more we are above, the better the model performs. So it's a very quick way to identify how good we perform. Now, if we measure the area under the ROC curve, the gray area here basically needs to be larger than 5 and as high as possible, closest to 1 preferably, if we have a good performing model. And that is what we express in the area under the AUC curve, which is almost a representative of accuracy, but it is class balanced. All right, here's an example. This is some research I did a while ago already, and it is classifying MIDI files per composer. So our class here is Haydn, Beethoven, and Bach, and we have a quite small data set. I first checked my class distribution. Bach, I had way more entries. Haydn and Beethoven a little bit less, so that's a nice graph to show. Then you see here I displayed the accuracy as well as the area under the AUC curve, okay, for a number of classifiers, all of them, which we saw in class, support vector machines having the best performance. Then what I also gave a little confusion matrix here, which shows me that there were 402 Haydn songs correctly classified. There were 24 Bach songs classified as Haydn, and the numbers that we're interested in, true predictions, are on this diagonal, while as the ones outside of diagonal are the wrong predictions. Okay. If you're interested to read more about this, you can click the link below. All right, that leaves us at the end of the classification lecture. Now, in the lab, we'll be doing some cool exercises in Python on creating classification models, okay, and properly evaluating them. So in the lab, you don't need to bring anything other than your computer. We will be using Google Colab, and I'll be sharing a notebook with you to fill in. That's it. If you have any questions, just ask on the course forum or send me an email, me or myself or the TAs. See you in class.